to welcome everybody here to the Capstone Design final briefings for this detail course. Some of you who were here last semester realize that this is the continuation of a two-course sequence where in the first course they design the aircraft, and in the second course we take them through into the RDT&E, the test evaluation phase. So we've got really kind of excited about these groups this year because it's the first time that we've had combined groups. This year we have an airplane, well, two airplanes, a combination airplanes that's going to be first stage and a second stage to orbit to take a small satellite into low Earth orbit and then come back and land and mate up with another one and take another one up there, which is a need that we have right now. And in those groups we actually have some of the space track students that are along with the aero track. So we have a combination in our design, which is really kind of exciting. And in the second group that you're going to see with the F4E, we have the mechanical engineering team that is working with us to design the engine for that aircraft. So we have the ME-AE combination in there. So without going any further, I'd like to have the panel members to introduce themselves and tell us a little bit about themselves.
My name is Ed Burnett. I'm a Senior Technical Fellow for Lockheed Martin Corporation. Work at the Skunk Works in Palmdale, and my specialty is modeling, simulation, and controls.
I'm Natalie Halverson. I'm from AeroVironment in Simi Valley, California. I have a background in aeronautical engineering, graduated from here. We do mostly UAV work. We have some EES, efficient energy systems as well. So looking forward to being here the first time.
Morning, I'm AJ Olson with Sierra Nevada Corporation up in Denver, Colorado. My background is mostly in aircraft loads and wind tunnel testing. I'm currently one of the lead engineers for one of our big manned ISR platforms.
Daniel Caraway. I'm from Boeing St. Louis Phantom Works. My specialty is in structural analysis and FEA.
Okay, thank you all for being here, and thank everybody for, we're going to start off today with the first stage on our two-stage to launch aircraft, because this is the aircraft that has to take that 75,000-pound second stage up to 60,000 feet and deploy that so they can fire their rockets and go into orbit. So the first stage is LaunchTech.
We got nothing left to present. Good morning, my name is Derek DeBreeze. I'm the DTL for the design group of LaunchTech. LaunchTech consists of myself, Kyle Hansen, Daniel Schreier, Steve Machine, Chris Enby, Michael Peterson, and Nathan Davis. So today we're going to do a brief introduction of what we've done, project description. We'll move on to our model development and fabrication assembly, and we'll move on to our first wind tunnel test and compare that to the data that we've made in Freeline. Then we'll make some recommended modifications to our wind tunnel model, and we'll show you the data we got once implementing those modifications. Then we'll move on to our structures, and then conclude with Luton's recommendations. So, description of our project. As stated before, this is a year-long project consisting of 2 semesters. The first semester in ERAU-420 was preliminary design. The first element for preliminary design was we were given an RFP, which will be shown shortly after this. After that, the first couple phases of preliminary design was conceptual design. So we were given parameters by which to design to. We created a design space and came up with an initial design. After that, we proceeded onto our preliminary design, where we refined our design and came in with an initial analysis and prediction for the performance parameters for our airplane. So for our RFP, the DoD released a RFP stating a desire for a 2-stage launch system capable of sending small satellites to low Earth orbit. The PT-1 was designed to be the first stage of this 2-stage system. The RFP is shown here on the primary screen. The motivation for this, of course, current launch systems is usually rocket-based and very expensive. Using an airplane as the means by which to get an orbiter up to a high altitude and then the orbiter get considerably cheaper and more reliable than using a rocket system. So LaunchTech was tasked with creating this first plane for this system. So our mission profile shown here on the primary screen. The Ambassador spacecraft, as designed by Genesis, will be mated with the PT-1 and take off from a conventional runway. Once we reach an altitude of 60,000 feet, the two vehicles will separate. The PT-1 returning to land, and the Ambassador spacecraft will ignite their engines and proceed to low Earth orbit. After they've completed launching their payload, they'll force re-entry and return back and land. So about our plane, the PT-1. After preliminary design, on the primary screen is a preview of the overall dimensions for the PT-1. Some things to know. The overall span is around 252 feet, which you can see on the secondary screen. The overall length is about 205 feet. And to discuss some of the elements and key components of the PT-1, we have 4 engines, GE90 with 115 feet engines, to give us the necessary thrust we have to perform the mission. Similarly, we went with a quad landing gear loadout, similar to the B-52. We took a lot of inspiration from the B-52, considering its heavy carrying capability as well as high altitude performance, and we simply upgraded. So moving on, for this semester, we were tasked with the detailed design phase, which is the RD&T, or research and development. For the first phase, we needed to convert our PT-1 and turn it into a test model, as well as develop a plan for our wind tunnel testing. Moving on to phase 2, we 3D printed our parts, fabricate the model, assemble, and then perform our first wind tunnel test to verify the performance parameters that we estimated back in preliminary design. After comparing the data and seeing where certain performance parameters can be improved, we proposed modifications moving forward. On phase 3, we develop these modifications and add it to the model, and then test those as well, and compare it back to our phase 2 data, and see if we did improve the overall performance of our airplane. After that, we go down and do a structural analysis for the key structural components for the PT-1. So I'd like to hand it off to Kyle Hansen, who will discuss the initial model, fabrication, and assembly.
Good morning, my name is Kyle Hansen, and like Derek said, I'm going to talk about the initial wind tunnel model, fabrication and assembly. So here on the primary screen, you're going to see a preview of our wind tunnel test model. This is a 1:1:1 scale model of the preliminary design PT-1. This model, or this scale, was chosen for 5 different reasons. We wanted to avoid wall effects. We wanted to prevent any blockage within the tunnel. We wanted to take overstressing the balance so it can produce more lift than the balance is capable of, than the balance can take. And then we want to reduce the cost of printing the model and allow room for an internal structure to improve the structural integrity of the model. So here on the primary screen is a comparison of the preliminary design PT-1 and the wind tunnel test model. The actual CATIA model was done by taking the one that was made in preliminary design and scaling it down within CATIA, and then we removed some of the unnecessary things like landing gear and the cockpit. And then we designed it so that the wings and the empennage could both be removable, and this is so we could do tail-off and body-only testing, and then we designed an internal structure for the model. So here on the primary screen is a comparison of the Ambassador and then the Ambassador model that we used in our wind tunnel test. We wanted to test with the Ambassador in the bay in the PT-1, so we scaled down their model into the one you can see on the right, the Ambassador model, and when we scaled it down, we had to remove the V-tail and the wings because the 3D printer could not print them. They became too thin. You can see we made a lot of changes to make sure it was mountable into our model, but on that bottom picture in red, you can see that the profile that extends beneath the PT-1 stays true to the original design. So we fabricated the 3D printed parts here at Embry-Riddle in the rapid prototyping lab. We had 13 parts printed. They were printed out of ABS plastic, and the printers have a tolerance of 0.02 inches, so this was taken into account when we were interfacing parts. Our total cost of printing was about $440. So now on the primary screen, you can see an exploded view of the 3D printed parts. You can see that we broke the wing into 4 different sections. This was so that it could fit within the build volume of the 3D printer, and we did the same thing for the fuselage. Parts 8 and 9, this is our empennage, and then our tail-off closeout. So when we did tail-off testing, we replaced the empennage with this other tail cone that didn't have surfaces. For the fabrication of the internal structure, that was done by members of LaunchTech here in the shop at Embry-Riddle. We ordered our raw materials from McMaster-Carr. We made up the internal structure out of steel rod, steel bar, and a aluminum T-bar. So the total cost of that raw material was about $42, so our total cost of our model was about $481. So here on the primary screen is an exploded view of that internal structure, and then the corresponding part names are on the secondary screen. Number 8, that is our fuselage support that we made out of the T-bar. That runs all the way from the forward fuselage back to the empennage, and that's our main support, and that's where we attach number 4, which is the mount, and that's how we mount it to the balance. Numbers 1, 2, 3, and 5 are our wing supports, and this was to stiffen our wings and to improve the integrity of that joint between the wing and the fuselage. So for the assembly of the model, on the primary screen, you can see the fuselage structure and how it kind of goes together. On the secondary screen is the mount. You can see that extends below the PT1 model about 2 inches, and this is to reduce the interference drag between the model and the balance. So after that, we assembled the actual 3D printed fuselage parts, and they were designed so that they have grooves that slide over the flanges on the T-bar to keep everything in place, and that was all epoxy to the T-bar and epoxy together. The mid fuselage is designed to slide into the forward fuselage, and that's where that 0.02-inch tolerance comes in when we're interfacing those parts. And on the secondary screen, you can see a top view of that body only. So one of the important parts of the design was that the wings could be removable. So we had to find a way to attach them to the body, but only make it temporary. So in order to do this, in order to make it so that the joint there was structurally sound and it didn't have too much wiggle, we used the steel rod. So the 2 steel rods slide into both the inboard wing and the fuselage. And then on the secondary screen, you can see a kind of a close-up view of that joint on the real model. And the wing, and that red dot, that's where a machine screw goes in with a nut on the other side, and that's what holds the wing to the model during testing. We also had to make the empennage removable. So on the primary screen, you can see how there's the empennage and then the tail-off closeout that replaces it, and they both connect to the fuselage support in the same way. They slide over the flanges on the fuselage support, and one machine screw goes all the way through the model, or through the empennage and through the fuselage support, holding that all in place. On the secondary screen, you can see what it looks like with that tail on and tail off configuration. So after assembling the model, we had to prime it, paint it, and apply tufts. So we chose black with the white tufts so that it showed up well in the wind tunnel, and that's for flow visualization. And then on the secondary screen, you can see how the wings come off and that empennage gets replaced with the tail-off closeout during that tail-off testing. So now Daniel Schreier is going to talk about the apparatus and the data from the first wind tunnel test.
Thank you, Kyle. I'm Daniel Schreier. I'll be discussing the first wind tunnel test and the apparatus we use for testing. Now, the wind tunnel we use for testing is the closed-circuit wind tunnel here on campus. And this wind tunnel has a 6-component ERAU pyramidal balance. And this balance is capable of a 50-pound load and is capable of an angle of attack sweep between -8 and 28 degrees. In addition, this wind tunnel balance has a beta sweep of -0 to -10 degrees of beta. Now, a little bit more on this balance. As you can see in the photo above me, the balance with the reference point marked. This reference point is the point at which all the CG is measured from. And in addition, on the secondary screen is a diagram of our model, the PT1, with the reference point marked and our CG relative to that point. And now to our test procedure. Our test procedure first involved loading the geometry into the model, into the computer running the wind tunnel. At which point, the wind tunnel was run with nothing on the balance, and after the tear data was collected from the balance, the model was then installed. And then once the model was installed, the test configurations shown on the secondary screen were followed. The model was tested between -4 to 18 degrees angle of attack, and the betas were tested between 0 and -10. The configurations tested were the full configuration, a tail-off test, and a fuselage-only test. and then the lift data from the first test. At the top in the blue above me is our prediction of the model's performance from prelim. Underneath that is the full configuration tested, and underneath that is the wing-only test. That is without the tail. At the bottom of the screen is the fuselage only, and the fuselage did not contribute significantly to the lift. Additionally, as shown on the secondary screen, our findings were that our CL alpha was accurately predicted. However, we determined that our maximum lift was over-predicted significantly. And in addition, we determined that our cruise CL was within 2 degrees of prediction. And then I'll look at some flow rates. Between 8 degrees and 10 degrees, stall occurred. At 8 degrees, the tufts began coming off of the wing, and by 10 degrees, almost the entire span was beginning to stall. At this point, we discovered that the wing is stalling at least 2 degrees earlier than our predictions showed. And now our drag data. We determined that our body drag at a minimum is at least 300% higher than we predicted. In addition, as I said, with the stall occurring at about 8 degrees, the separation drag contributed substantially more than predictions showed. And as well, the tail drag was significantly less than we predicted. We over-predicted significantly with the tail. And then some more flow visualization of the fuselage. We discovered along the nose of the aircraft, of the model aircraft, the tufts were beginning to separate at low angles of attack. And in addition, on the tail ramp to the left, at low angles of attack, there was also separation in the tufts. However, the biggest problem is in the middle, where the ambassador bay is. And we saw that at every angle of attack, the tufts were getting pulled into this bay. And you can see in the tufts that they actually have an angle to them. And this occurred at all angles of attack that we tested. Now to our drag polar. As I said before, our stall occurred much earlier than we predicted, and the drag increased substantially higher than we as well. And as a result, our body lift is very low, and it contributes substantially to drag. And now, additionally, our moment data. This will not be presented during this presentation. We misentered our CG incorrectly, and we were not able to salvage this data, and therefore it will not be shown. However, our second wind tunnel test, we corrected the error, and that will be shown later in this presentation. Now, Kasim will talk about the modifications we made for the second wind tunnel test.
Thank you, Daniel. I'm Kasim Hashim, and I will go over the modifications on the PT1. So the first modification on the PT1 was adding the winglet to the PT1, and the purpose for that is to increase the efficiency for the PT1 wing. Or mainly reduce the induced drag for the wing. In the secondary screen, you see the CATIA drawing for the winglet and a side view for that. The fabrication for the winglet was created by sweeping the airfoil vertically up with maintaining the same thickness and core length for the airfoil to keep it structurally sustainable during the wind tunnel test. And on the secondary screen, you see the initial wing for the PT1 before the wing was added, and the second one is the modified wing. The second modification was on the vertical size. We resized the vertical or the empennage for the PT1 because of the incorrect midline fuselage used in the CATIA model. And also we want to reduce the weight for the PT1 and also reduce the total amount for drag. In the secondary screen, you see the modified vertical size or vertical tail for the PT1. So the reductions in size was 20%, with maintaining the same aspect ratio for the vertical side or for the vertical tail, with maintaining the stable lateral directional stability during stability data. Based on that, the fabrication process was reprinted the new wing with the winglet and the new empennage with the reduced vertical size. After that, the new wing assembly made it by the model team, and also the parts were sanded and primed at the fabrication lab. And finally, the painted, or the parts, or the new parts were painted. In addition to that, the new metal wing support were provided for the new wings and the empennage. This is another modifications to the PT1. This happens accidentally when the plastic wing joiners failed during the second test, or before the second test, because of the weak part made by the 3D machine. So the modification on that was gluing the plastic joiners of the wing and permanently affix it to the fuselage. And for future recommendation, a metal wing joiner should be used instead of plastic. Organic will continue with the stability data.
Thank you, Kasim. I'm Chris Emke, and I'll be going over the rope and stability data for the second test. On the primary screen, we have our test configurations for the second test. As you can see, we did alpha and beta sweeps for the full configuration and for the configuration with wingwits. And we only did a beta sweep for the new tail. On the primary screen, you can see the CL alpha plot. We overpredicted the lift, as was said before. Winglets did help correct this issue slightly. However, they did not quite meet our CL max of 1.3 that we predicted. On our secondary screen, you can see the new VM diagram made with the new CL max from the experimental data. The only thing that has changed is that the stall lines have moved to a lower velocity now. And now on the primary screen, we have the CM alpha plot for the second test. We are unstable until a stall happens at about 8 to 10 degrees, at which point the aerodynamic center shifts after the CG and we finally become stable. One thing to note is that we need about 20% more static margin in order to meet our stability predictions. And now on the primary screen, we have the CM beta data for the second test. Reducing the vertical tail ended up reducing the experimental coefficient by about 25%. We are still slightly more stable than we predicted. However, this is not considered to be a large issue for PT1. So for our CL beta data, every time that we input the beta into the program crashed. So we ended up having to make a correction for rolling moment contribution due to the weight of the model. As you can see on the secondary screen here, as the stability axis, or as the model shifts outside of the stability axis, the program would actually have to shift the stability axis back into the CG location in order to prevent a rolling moment from occurring, and use the equation on the primary screen in order to correct for this. W is the weight of the model, X is the distance between the CG and the pin, and that's all over the dynamic pressure multiplied by the planform area and the span of the wing. And now on the primary screen, you can see the CL beta data, the corrected CL beta data. We are slightly more stable than we predicted. However, this is again not considered to be an issue for PT1. And the new tail and the winglets had very little effect on this coefficient data. And now Michael Peterson will present the JAG data.
Michael Peterson, I'm going with the drag data for the PT1. In the second round of testing, we want to see what the winglets effects would be on drag as well as lift. Experimental data showed that there was a slight increase in drag with winglets as opposed to a decrease that we were expecting. This increase in drag, we believe, is primarily due to the ineffective design of the winglets themselves, as they were designed with structural support in mind first instead of the efficiency of the winglets themselves. Shown here is a drag puller for the initial model and winglet test. Again, there is a slight increase in drag for the drag puller from the winglets, although they follow near the same trend until roughly around where the initial model reaches its CL max. While the winglets did improve the CLmax value of the PT1, as the CLmax value is associated with a large amount of drag, this increase in CLmax does not improve the performance of the PT1, not benefit its ability to make the mission. More in mind about the winglets. Again, these winglets were designed for structural integrity first, as originally with the scaling value of the PT1, they became too thin to realistically print. As such, they ended up being designed as the wing themselves was the appropriate thickness that could be printed and turned up at a 90-degree angle. As these were the actual wing turned up, it ended up being an airfoil curved in about 5 degrees into the flow. I believe this is a partial reason for the increase in drag. Also, in addition, they're extremely large in comparison to what winglets should be. Their overall surface area is roughly the size of what our original vertical tail would be. Also, when we reprinted the wing to make addition to the winglets, there was a printing error for the nacelles on the plane, as the initial only one of the engines was printed 4 times instead of 4 different engines. We believe this to be a partial increase in the drag, as turning flow would happen into the nacelles as there's no air being sucked in from the engines. We believe this increased drag might have happened to the original model as well, as again, normally engines would be able to provide maybe a reduction in this turning flow drag. So here's the thrust available versus thrust required at sea level. Thrust required being for the original frequency values, experimental, and the winglet data. Initially, the PT1 was expected to reach 0.85 Mach at this altitude, and the experimental data shows it's reduced to 0.65. The wings have an increase in thrust required, and this trend exists at all altitudes. So here's the thrust available thrust required for 30,000 feet. This altitude represents the last 10,000 foot mark where the PT1 has enough excess thrust to be able to run with only 2 engines. Originally, the PT1 was expected to be able to go so fast that the engines would not be able to perform due to shock waves forming in the actual engine themselves. However, experimental data shows that the maximum speed is around 0.7 Mach, which means that an additional manual would not need to be provided to the pilot to prevent from overstressing the engines. Shown here is thrust required for thrust available for 50,000 feet. This represents the last 10,000 foot marker where the PT1 was capable of flying. We have a maximum SS power that's 338 feet per second at roughly 0.5 Mach or 0.6 Mach. And they have a speed range of 0.55 to 0.65 Mach. Experimental data shows that the maximum altitude will be 51,000 just above this. However, with the addition of winglets, the ability to even make the 50,000 foot altitude would not be possible. So here's the excess power for the winglets, showing that right now our maximum altitude with the winglets attached would be 47,000 feet, reducing a critical parameter of the PT1's design, the altitude that it's capable of reaching. As such, the winglets in addition is really a net degrade in performance for PT1. So here's the excess power for the final configuration, the maximum altitude of 51,000 feet, and a maximum speed of 440 knots for airspeed. Although the PT1 cannot reach its RFB altitude of 60,000 feet, it is currently able to outperform any aircraft capable of attempting this mission. And now Nathan Davis will go into the structural layout and analysis of the PT1.
Good morning, my name is Nathan and I'll be going over the structural analysis and layout. We'll begin with the PT1's Venn diagram. Note that this is a structural Venn diagram. It's plotted in knots equivalent airspeed as opposed to true airspeed. And the limit at the far end is a dive speed, not a key limit. Some other parameters to note from this. Then max, which is the structural load limit, is 2.19, and the negative structural load limit is -1. As well as we have a corner velocity at 167 knots equivalent airspeed, a cruise velocity at 227 knots equivalent airspeed, and a final dive velocity at 314 knots equivalent airspeed. And now to begin the actual internal structure of the PT1, we're beginning with the fuselage. The fuselage has skin, stringers, and ribs. The skin is an 1/8 of an inch thick and is made primarily of graphite epoxy. And the stringers are also made of graphite epoxy, and with the exception of a few near the Bay Area, which are handling extra stress from the Bay Area. Stringers are 1 inch squared, and the stringers near the Bay Area are 2 inches squared. The ribs are perpendicular to the stringers and run along the length of the fuselage and are made of aircraft aluminum. Now, the wing structure of the PT-1, we have skin, stringers, ribs, spars, and fuel tanks in the wing. The skin is an 1/8 of an inch thick and is made of graphite epoxy with the exception of the leading edge. The area around the leading edge is made of aircraft aluminum to resist the effects of air heating. The total area of the stringers is 278 inches squared, and the stringers are made of graphite epoxy. The maximum stress for these stringers is compressive stress of 45.8 KSI occurring along the bottom of the wing, and a tensile stress of 45 KSI occurring along the top. The spars of the wing occur at 25%, 47.7%, and 70% of the chord. These spars are made of aircraft aluminum, and the fuel tanks occur between the second and third spar. PT-1 has ribs spaced 24 inches apart with false ribs in between. These false ribs are just the leading edge portion of the rib and are here to prevent leading edge deformation along the front of the wing. The ribs are made of aircraft aluminum. And then I move on to the empennage structure of the PT-1. The skin is an 1/8 of an inch thick. It's made of graphite epoxy with the exception of the leading edge again. This is to resist the effects of air heating should they occur. And the stringers here, we have 32 inches squared total area for the horizontal tail and 30 inches squared for the total area for the vertical tail. And the stringers are made of graphite epoxy. And the spars here occur at 25%, 50%, and 70% of the chord. And the ribs, again, are 24 inches spaced apart with false ribs in between. And the ribs are, in this case, both the spars and ribs are made of graphite epoxy as well. Now, if you look on the primary screen, you'll see tables for the horizontal and vertical tail. The horizontal tail, the max stress occurring is 44.6 KSI, and that is both compressive and tensile. In case of the vertical tail, the max stress is 40.6 KSI, and that is again both horizontal and both compressive and tensile. Now, you'll see a picture of the PT-1's main wing loaded in bending in ANSYS. The max stresses here, if you see on the secondary screen, are 55 KSI and a negative 61 KSI for the compressive. These are compared to a theoretical calculation that we made using Shrink's approximation and with the G loading of 2.19 and an idealized wing box calculation. You can see the percent differences as well. Now here in this, is the same wing loaded in shear instead of in bending. As you can see here, the shear stress found for the PT-1's wing was 6.89 KSI, whereas our theoretical calculations calculated 41 KSI. This is a large discrepancy, percent difference. However, the PT-1's wing was designed to this theoretical calculation of 41 KSI, which means the wing is actually very resistant to shear. And now, Derek Trees will begin labor and accounting.
Thank you. Thank you, Nathan. I'll be going over labor and accounting. So here are the total hours that we committed to this semester. The top line is the predicted hours based on a model of 2 hours outside of class for every 1 hour in class. The actual hours shown falls just underneath that. Here are our current design costs. Currently, amongst our team, the total costs for our various categories is around $77,000. And now a breakdown of our hours. On the primary screen, you'll it is shown that the majority of our time that our team has spent on this project is in engineering and administration work. On the secondary screen, it is shown that the majority, or the cost breakdown for our group, the majority of it, again, is in engineering and engineering management. Now I'll go over conclusions and recommendations. From what we've concluded from our wind tunnel test results is, in its current configuration, this aircraft produces too much drag for flight at 60,000 feet. From our flow visualization, it does indicate there are problematic regions on the fuselage where flow is indeed separating, and the area in front of the ambassador bay in which the flow is going into the fuselage of the PT-1. From our test, it was also removed that the design of our winglets were poor and causing more problems than they had addressed. From our stability portion from our wind tunnel data, we found that our aircraft was unstable in pitch. For lower angles of attack, we had a positive CM alpha and would only go neutrally stable as soon as we went around stall, which we do not want our airplane to be stalled or stable around stall. So for our recommendations for the first flight test article, the PT-1, we want to modify the area in front of the bay to have an additional panel that can be retractable to be able to close off right in front of the ambassador such that flow can't enter the fuselage from that point. Additionally, we would also like to commit further time in research and development for winglets, since it is more generalized and common knowledge that winglets should improve performance, and it has become apparent that you can't just simply sweep a wing and get a winglet out. Additionally, to address our stability problems for our pitch stability, some of the modifications that we could propose is to move our fuel tank's locations from its current second and third spar locations and move them forward, thus shifting our CG forward. Additionally, since we resized our vertical and gained some, or reduced the weight back there, we could consider resizing the horizontal tail as well. Any questions?
Okay, thank you, panel members.
All right. Very fun to deal with wind tunnel data, and going through and trying to figure out what all you did wrong. If there is one thing that you think you kind of missed, what would you think that is?
The biggest thing that I wish that we could possibly spend more time analyzing and kind of addressing is for a lot of our stability data, we had very wide fluctuations, and other times it was very stable. So far, we don't really have an explanation for why the data would start going zigzag in some places and relatively calm in some places. So analyzing effects for perhaps maybe wing vibration could be causing such changes in our data there. But unfortunately, we didn't have to spend the time to be able to figure out the vibration modes for our wing. So
Yeah, frequency domain aerodynamics are not fun. But in your ability to predict, you had a very non-aerodynamic characteristic of your airplane. If a large bay, bays cause lots of separation, acoustic, frequency domain aerodynamics, how did you account for that in your predictions?
Unfortunately, in preliminary design, we're first developing the bay. Our predictions for the fuselage were assuming that the bay itself was not contributing largely to changes in the overall design of the fuselage. Once we hit wind tunnel testing, we realized the full extent of the mistake in that prediction.
I guess the one that's, once you dropped the vehicle, the Ambassador, things would really change again. Did you look at that part of the wind tunnel testing?
For the preliminary configuration for PT-1, once we drop off the Ambassador, we do have doors that close off. So
okay.
The bay would essentially be closed after we jettison our payload. However, for the brief moment of time between right after
thought would be some sort of breakaway structure, so you would have a continuous structure aerodynamically for the launch and then close the doors afterwards.
Yeah, I would have liked to have seen some of that data, the payload versus no payload. And then additionally, did you take into consideration your mounting structure is in the payload area? So it's going to change some of your aerodynamics related to that payload bay. I thought you guys did a great job presenting the data that you had from a program management standpoint when you presented labor costs and hours spent. It's great that you track that. I will tell you though that the labor costs that you present for program management and administration on a real program, you get crucified. Right. It's just under 20% is still high. So, but you guys did a great job.
Good work. I'm going to pick on your wind tunnel data extrapolation a little bit. Go for it. All right. I appreciated your discussion on the sizing considerations for how you chose the size of the model itself. How did you then take those scale effects and translate them into a full-scale airplane result?
Since between preliminary design and the early phases for detailed design, one of the major parameters that we're using to compare the more non-dimensionalized characteristics, so things like the drag coefficient, lift coefficient, stability data. So once we got to like our drag coefficient, we were able to put that back to the full scale for the model.
Did you consider any Reynolds number differences between what you tested in the tunnel versus full scale?
We did, but I'm afraid to answer that. No, we did consider Reynolds number differences, especially for high Reynolds number effects, the effects of having the tape and the tufts can trip the boundary layers, and that's one of the things we wanted to do, try to at least emulate the Reynolds number effects.
Okay, that's a perfect segue into the next question.
Sure.
All of your force and moment data was done with tufts on?
Yes.
Why?
We were not instructed as to take them off. Additionally, especially with doing the beta tests and things like that, there are regions on the DC line where, especially with the winglets, we want to be able to observe like different phenomena that were occurring on the various regions on the airplane.
Okay, in general, they're two very separate and very distinct sets of tests. You're going to go through and do a full visualization series so that you can kind of get a conceptual feel for what's going on, and then you're going to do a force and moment set so that you can actually get data that you trust. In general, tufts as a boundary layer control manner for models is not really the way to go. I completely understand all the time constraints, and that's, honestly, that's what it really comes down to, is you've only got time to sit in the tunnel for X amount, not twice as long in order to do both of them. So I totally get that, just something for you guys to know. When it comes to the data interpretation, just think a little bit further down the line about how you actually need to correct that. I haven't seen since I've been here 13 years ago, anybody has ever done really a full tear interference set to help correct the force and moment data on the models. And that's complicated, but it's one of those things that's necessary too. Overall, you guys do a really good job. I appreciate that. I want to make one other comment. You also learned a very valuable lesson on winglet design. Absolutely. People think that winglets are easy, and they are surprisingly complicated, and you need to put a lot of time and effort into a winglet design, or you almost always wind up hurting yourself instead of helping. You have to consider things like cant, toe, size, shape, sweep, airfoil. You almost can't, more often than not, shouldn't use a non-symmetric airfoil for something like that. Winglet design is very difficult, so I'm glad you guys picked up on that pretty quick. Good work.
All right. I'll reiterate, very good job. I felt like you guys answered a lot of the questions of why. And that's what we're asked to do all the time when you get out in the industry. Especially, I'd say, some of the younger guys, they want to know if you really understand what you're doing. So I felt like there were parts where that could have been better, but also overall, really good job. So I'll ask about some of the structures. One thing comes to mind is when this payload separates, that's a, I guess, pretty big CG shift potentially. Was that taken into account at all?
Yes, in preliminary design, we tested every possible configuration in terms of having the ambassador inside of us, having it lowered, and having them jettisoned. We try to make sure that once we lost such a heavy payload that we wouldn't lose our longitudinal stability.
Okay. So the, I guess, bigger impact to the structure there is you have a massive hole in your fuselage. Did you guys consider what that impact would be, or do any stress analysis on the fuselage for that?
We did consider that the large bay would have a pretty significant impact. However, in terms of time requirements for our structural analysis, we were limited to how far we could go, but that's definitely one of the things we would love to explore.
Yeah, so a part of that, I guess, I think I would have liked to have seen is the thought process of the load path there. That's kind of one of the key, I'd say, aspects of structures is you can do all the FEA stuff you want, you can do all the analysis you want, but if you don't have a good load path, you're not going to have a good product. And so I felt like there you needed to, I guess, focus a little bit more on, we're just going to slap this thing on the bottom of the fuselage and go with it. So the last thing I wanted to ask about, on the FEA results, it was slide 62 and 63. You showed percent differences with theoretical calculations, 22%, 33%, and 600%. So can you talk about any red flags that threw for you guys with your model? Maybe how accurate it was, that kind of thing?
For the bending stresses specifically, the 22 and 33% regions, there are points on the stringers where those were kind of like the peak, whereas the majority of the stress in the stringer itself was more around the prediction. For the shear stress, however, that large discrepancy was something that we had not anticipated. And we ran our finite element model over and over again, checked our spreadsheets over and over again. Finding the discrepancy between the two, we ran out of time to find, but we do know that it exists, and it's something that we want to find.
Yeah, no, that's really good that you guys started looking into it. And I asked what some of the, I guess, values or parameters you looked at is to try and figure out what was wrong potentially, like deflections, that kind of thing.
Right. For when we were doing our spreadsheets too, for the idealized wing box, one of the things that I noticed that was difference between the ANSYS model that we made is the idealized wing box didn't assume sweep or taper. We factored that being a potential contributor to the difference in shear. Additionally, we took into account perhaps differences in terms of the spreadsheets loading and how we loaded in ANSYS, in terms of what forces we used, which could be a huge contributor, as well as constraints for the ANSYS model as well.
Very good. One thing to be very careful about with the FEA stuff is the actual element selection itself. You can use many different things. It looked like you guys were using shells and bars.
Shells and beam.
Shells and beam. Okay. So with shells, there's a very important lesson learned that if you guys go into structures, you'll learn it very quickly. But a try element is a bad element. It's a no-no. You have to use it sometimes, but that's there's ways around it that we go about doing it. So it looked like you guys had a pretty decent match from what I could tell. So that was pretty impressive, actually, especially using a tool like ANSYS. Very hard to use to get good match quality. But in addition to that, something you guys could look into later, and time constraints kind of hindered that, but definitely looking into the actual mesh dependency of the solution itself. But good job.
Thank you.
So I missed the preliminary design. What airplanes did you look at? What combination of vehicles did you look at that also draw as your inspirations?
Several vehicles we took a gander at were other platforms for like two-stage launch systems, so like White Knight 2, for example. Stargazer with the Pegasus rocket, since they were also performing very similar missions to our own, except there's distinctive difference between the Pegasus rocket and the Ambassador is the rocket is, do it once and over. The Ambassador would be reusable. So having the capacity to carry something that's considerably heavier kind of changed kind of our focus more toward a combination of these two-stage systems as well as like a heavy bomber.
So you didn't go back to X1 and try to look and see why the X2 was outside the airplane?
We
And
did
then-
take a gander at that.
And the space shuttle's the other one.
Yeah.
Put it on top.
Okay, thank you, guys.
Thank you very much.
Our next group will talk about